Hello, in this presentation we'll talk about how a C++ program uses OpenGL shader programs to draw a triangle on the screen. So the talk will focus mostly on the conceptual levels, but will include some actual C++ code, or at least some snippets of C++ code, and we'll give the complete shader programs for the Vertex and Fragment shaders. And a future presentation will actually show more of the code on the computer. But for this presentation, we'll just stick to the whiteboard and try to keep things as conceptual as possible. You can find this material in Chapter 1 online, and the Simple Draw Modern program on the book's website contains a complete working program as a first example of how to use OpenGL with C++. And included with that program, there's a web page explaining all the code in the program. So you're encouraged to look at that as well. All right, so what we want to do in this particular example is we want to draw a triangle. And I'll use the points here. The triangles will have points 2, 1, 2, 2, and 0, 2, the same as we did in a previous presentation. So here's the triangle. We're going to draw it filled in. And we're also going to give the triangle some colors. So I'm going to make the first vertex that I put on the board, 2, 1, is going to be red. And the code for red is going to be 1, 0, 0, 1 for red, 0 amount green, 0 amount blue. The next one will be green. And the code for that is going to be 0, 1, 0. It contains 0 amount of red, amount 1 of green, 100%, the maximum, and 0 of blue. And then the third corner will be blue, which has the code 0, 0, 1, which is the max amount of blue and no green and no red. So this is the familiar RGB specification of colors. And when we draw this triangle, the colors are going to get averaged. We're going to give the colors to the vertices. We'll say this vertex is red, this one's green, this one's blue, and then the colors in the middle of the triangle are going to be averages of these things. So like the color right here in the middle of the line between blue and red is going to be the average of these two things, which is 1/2, 0, 1/2, which is a sort of a dark magenta color, or somewhat dark magenta color. A magenta is like a purplish, almost reddish purplish. Blue is usually a very dark blue when we're talking about RGB colors. Between blue and green is going to be the color 0, 1/2, 1/2, and that's a slightly dark cyan color. And cyan is a fairly, usually I would say it's a bright blue, but it's really midway between blue and green. And over here on this side, somewhat surprisingly, the color 1/2, 1/2, 0 turns out to be yellow. In other words, when you take the average, a slightly darkish yellow. So when you take the average of red and green, you get something that looks yellow. Full-on yellow would be, fully bright yellow would be 1, 1, 0. So this is 1/2, 1/2, 0. So it's half saturated red, half saturated green, and no blue. The middle point would be, have the value 1/3, 1/3, 1/3, which would be some sort of gray color. So now we're going to talk about how the C++ program works with OpenGL to draw this triangle. So step 1 of the process is to build a C++ array holding the vertex attributes. And the vertex attributes, that means numeric properties of the vertex. And the vertex attributes will be for the position and the color. So the kind of command we use is something like the following. We'll say float verts, and square brackets for an array, and then we give a list of the data. And so the data here, we're just going to list the x, y positions of each vertex and the RGB color values for each vertex. So it's 2, 1, 1, 0, 0. That's the position of the first vertex as 2 floating point numbers, and then the color of the first vertex is 3 floating point numbers. and then 2, 2, 0, 1, 0. That's the position and the color of the second vertex. And then 0, 2, 0, 0, 1. That's the position and the color of the third vertex. So we've got first vertex, second vertex, third vertex, position, color, position, color, position, color. And this just builds an array in C++. So step 2 of the process is that we load the data now from the C++ array into the OpenGL buffers, which should end up on the GPU, on the graphics processing unit. So the C++ array was created on the CPU, the central processing unit. We want to get this stuff into the GPU for doing our graphics. So there's a lot of commands for this, far more than would fit on this board. So I'm just going to explain the conceptual part of the commands, a subset of the commands, and later on in the next video we'll see more details about a complete program and how it works. But there's 3 basic commands I want to talk about now. So first of all, there's the GL buffer data command. This is a C++ function. And what GL buffer data does is it loads the data from the C++ array into the OpenGL buffer. And so for this, the first parameter of GL buffer data is GL buffer array, which tells us where to send the data. It goes to an object called the buffer array. Sometimes this is called a vertex buffer object, VBO. So vertex buffer object, VBO, is what people frequently call a vertex buffer array. But vertex buffer array is just a keyword here. And then we have to specify how much data to upload, how many in bytes. So we'll say size of verts. And this is the amount of data to upload in bytes. So there's size of as a C++ construction that takes in an object, like the array in this case, and gives you the size of the object in bytes. And then we have the address to upload the data from, which is verts. So it says telling it upload starting from the beginning of the verts array, size of verts, many bytes. And then finally we need to tell OpenGL some hint about how we're going to use this. So we'll say GL static draw, which tells OpenGL that this is some fixed data that we're not going to be changing very often, to give it a hint as how best to do its data management. So again, GL buffer data takes the data from the C++ array and loads it into OpenGL's buffers. Now we need to tell OpenGL what we uploaded into the buffer. This just put a bunch of bytes there. So to tell OpenGL what we uploaded into the buffer, we use 2 commands. There's GL vertex attrib pointer. You will see that OpenGL commands can be awfully long. So this is no exception, and they do get longer. So this says something about the vertex attributes that were just uploaded in the GL buffer data. And we're going to have the following parameters. So it's 0, let me just write this out first, and we'll go through it. 0, 2, GL float, GL false, five times size of float, comma, void star 0. So let's run through what all these different things are. So 0 is what's known as the location, and this identifies it as the XY coordinates. In this particular case, we'll see why. It identifies it as XY coordinates. But what this really means is we'll see in a little bit that this is something inside the shader program that this is. So 2 is the number of data items that are part of this location. And 2, in this particular case, it's X and Y. So we've got XY for position. So we've got two data items, an X position and a Y position, an X position and a Y position. Don't worry about the GL false. This says something about what we do with conversion to integers. The GL float says we're adding two floats. So again, this part here, 2 comma GL float, says there's two floating point numbers that make up the data in location 0. And the location 0 will correspond later to XY component of the position. And then this is what's known as the stride. So the word stride means like the length of a step, how long you step. Striding is stepping. And so a stride here, this says 5 times size of float. We go from, here's the first vertex, 21100. Here's the second vertex, 22010. And the stride is this length here. There's 5, you go from here to here, that's 5 floats. So it's 5 times 4 usually is the number of bytes used for a float. So it's 20 bytes in this particular case to take us from the start of one position to the start of the next. So the stride is telling us how far apart the data is in the array for each vertex. And void 0 is the starting position in the VBO. That is where the first XY appears in the VBO measured in bytes. That tells OpenGL that the data for position, or for location 0 data, starts at location 0, and you can find successive vertices by going that many steps. And then we also have to turn this on, so we need another command. So we say GL enable vertex attrib array 0. And the 0, this is another OpenGL command, the 0 means location 0. So this 0 here is the same as this one here. So what we've done with these two commands is we've told it where the data is for location 0, and now this command says use the data in location 0. And these two commands then set up using XY values for position, tells the program where they are in the array. Okay, so I'm going to now, you might pause here and think about this, and I'm going to then change the board a little bit on you. So this was for, let me write it down here. This is for the XY values. So now I'm going to do a little bit of magic of the eraser and show you how you would change this for the color values. So the color values are going to be, let me just start erasing stuff. They're not going to be location 0 anymore. They're going to not have 2 data items. They're going to have 3. The stride is still going to be 5. And then the starting position will be someplace different. So let's fill in what this is going to be. I'll use another color in the hopes you can see the difference in the color. So the location, whoops, I changed both of them. So the location is going to be location 1. So location 1 will hold color value. And there's going to be 3 data items because there's RGB. So now it's 3 data items. RGB values, because we've got 100, for instance. They're still floats. This conversion stuff from integers we still don't care about. The stride is still the same because, see, we're going from the start of one color to the start of the next. It's still 5 floats to go from the start of one color to the start of the next. So the stride hasn't changed. And now the starting point is no longer, before we had void star 0, but now the starting point is starting here at the 3rd float. So we'll use, as the final parameter here, we'll use void star 2 times size of float. Close parentheses. So this will tell it start the data from location 8. 2 times size of float will be 8 bytes from the start of the array. And so this says the color starts here, there's 3 numbers, and to get to the next color you jump 5 numbers up. And then this is location number 1, and we enable location number 1 to read from the array. So that's how the data gets stored in the array. It allows you to very compactly store data, upload a lot of data all at once, and gives you a method then to identify what data is where. So all of this has to mesh then with the shader programs that I'm going to describe next. So step 3 is going to be compile and link shader programs. This is going to be a big step to describe, so I'm going to hold off on this for just a moment and describe step 4, and then I'll come back to step 3. So step 4 is going to be draw the triangle. And this is done with a C++ command. Use this. GL draw arrays, similar to what we described before. So with the option here, GL triangles, we've only got one triangle, but we can still use GL triangles. And we 0, 3. And 0 means start with the vertex number 0 in the array of data that was uploaded to the GPU. So with the GL buffer data command, we uploaded some data. The first vertex in that is vertex number 0, and we start the triangle with vertex number 0, and we use a total of 3 vertices. Because we use 3 vertices and we're making triangles, that means there's 1 triangle. So that'll pick out and draw those things. So this then invokes the shader program to render the triangle. Okay, so now let's come back to step 3, and I want to give you some examples of what shader programs look like. So I'll write these out in full. Again, they're very similar to what's in chapter 1, with some slight differences. So next I'll show you the Vertex and Fragment shader. I'm going to give you the full code for those. They're very short in this case. They're very similar to programs that you can find in chapter 1 in the textbook as well, or the program in Simple Draw Modern. For this program, the shader program consists of 2 shaders, the Vertex shader and the Fragment shader. The Vertex shader will run once on each of the 3 vertices. The Fragment shader will run once for each pixel covered by the triangle. So let's start with the Vertex shader. And as I said, it runs on each vertex. So for each vertex, it'll take the XY position of the vertex and the color. And here's the code. So the first line just declares the version number. It's version 330 core. And this gives the GL SL version of the language that's being used. So GLSL is the GL shader language, GLSL, and it's the language, it's a C++-like language that's used to write shaders. So in this case, we're using the core features of 3.3. The first 2 lines after that describe the inputs. So layout location equals 0. In means an input. Vec3 means a vector of 3 floating point numbers, and I'll use the variable name vertpos, semicolon. So this says there's an input data item called vertpos. It's a vector of 3 floating point numbers, and it's identified as location number 0. Location number 0 corresponds to the location number that we used in step 2 with the C++ commands when describing the contents of the VBO. And then, so this is a vec3. It's actually got x, y, z values. The z's are just going to be set to 0. In the VBO, we only gave x and y values. The z value is automatically set to 0 for you by OpenGL. And then the next line gives that the color is also an input. Layout location equals 1 in vec3 color. And this is going to be a vector of 3 floating point numbers, RGB values, in the range 0 to 1. And these data items for each vertex has x, y, z values and RGB values. The output, there's 2 outputs. One of them we declare explicitly, out vec3 the color. Could be any name you want it to be, but it's just, we're outputting a vector 3, vector of 3 floats. It's named the color. And now we give the program. Void main, open curly brace. Now, the main output for the vertex shader is a variable called GL position. GL position is always a vec4, a vector of 4 floating point numbers, and I'll just write it this way. Vec4 of, and the first thing I'll just give explicitly the parameters, vertpos dot x minus 1, vertpos dot y minus 1, 0, 1. Okay, so what's going on here? We're outputting a vector with 4 components. It's got an x component, a y component, a z component, and a so-called w component. So this is an x value, this is a y value, this is a z value, and this is a w value. We'll learn later in the course what the w value means, but now we'll just force it equal to 1. The x, y, z values are supposed to be in the range minus 1, 1. So x, y, z are supposed to be in the range minus 1, 1. Now the input values, if you saw the data, they're between 0 and 2. So when we output GL position, we're going to just subtract 1 off the x coordinate and y coordinate. That'll shift their values into the range minus 1, 1. The point is, we want them to be in the range minus 1, 1 to show up on the screen in the final image. So this is sort of standardized coordinates for the image. When we're drawing things on the screen, we renormalize all x, y, z values to be between the range minus 1 and 1. So GL position is giving the position on the screen of the vertex. The other output value is the color, and we just set the color equal to color. We just pass the color value through. The input color value becomes the output color value. We don't change it in any way at all. We changed the x, y positions, but we didn't change the color positions. And I maybe should have mentioned earlier, this is very C++ syntax. So vertpos.x, you can think of vertpos as an array of length 3 or as a data structure with members .x, .y, .z, and .w. Okay. And that's the end of the vertex shader. As I said already, it's run once for each vertex. Now the outputs of the vertex shader get sent to the fragment shader. So let's talk about the fragment shader. Fragment shader is run once for every pixel covered by the triangle. So the triangle here, the vertices end up somewhere on the output image. The corresponding triangle covers some of the pixels, and for each one of those pixels we call the fragment shader. So let me give the source code for that. So the first line is still the # version 3 30 core to say what language version we're in. We declare the inputs in vec3 the color. So this is saying that the input color to the fragment shader is taken from the output color of the vertex shader. Now, as I'll discuss in a minute, that's not quite true. There's some sort of averaging going on first, but let's just pretend for the moment that color went through. The next line declares the output variable, out vec4. The output has to always be a vec4 object, and I'll just call it pixel color. So this output value will be the color of the pixel that corresponds to this instantiation of the fragment shader. And then we have void main, and we'll set the pixel color has to be a vec4. And I'm just going to define this program to just pass through the input color as the output color. The input color was a vec3, not a vec4, so we'll change it to be a vec4 by saying vec4 the color, comma 1. So the 1 there indicates no transparency. So this 1 is that's no transparency. The 1 gives it how opaque the image is. So we just take the RGB values that were in the vec3 variable the color. They become the RGB values for the pixel color, and we set the transparency or alpha value equal to 1. This is sometimes called an alpha value. And that is the whole fragment shader. So now let me describe this averaging process that goes on. As I said, the outputs from the vertex shader become the inputs to the fragment shader. But now what happened here is the fragment shader, the colors were for these 3 corner vertices. But if we have a pixel, say, right there on the edge between the red and the green edge, the fragment shader is run on this pixel. The color value that comes in will be the 1/2, 1/2, 0, as I wrote earlier, that corresponds to a slightly dark yellow color. It's obtained by averaging the red and the green in this case because it's on the boundary containing the red and green vertices. More generally, a pixel in the middle will have a color that's the average of the red, green, blue vertices, where the colors are averaged smoothly across the triangle, so it's green, gets green into this corner, red into that corner, and blue into this corner. Okay, so that's it for this presentation. The next presentation will go briefly through the Simple Draw Modern program and show you the complete C++ code that was used, just so you can see an example of how a complete program runs. Thank you.